All right, so let's start. Today we start with a new topic, which is PN junctions. And although it's a new topic, but today's lecture will be more of a revision of the concepts that we've already covered, drawing energy band diagrams, using Poisson's equation, except in the context of a PN junction, right? So don't take it as a new topic before the midsem. Take it more as a revision of things that you already know. Okay. All right, so let's start. There are a couple of things that you guys are already familiar with, which this is all right. Okay. Symbol of the diode you're already familiar, PN junction diode, right? You know that it's a diode here. We often schematic representation of the diode, we draw it as a P and an N and a contact here and a contact here. This is a slide that you would have already seen. A PN junction is more like what you see here, a two-dimensional view of the PN junction here. So we have an N region. So you may N region here, and P region is diffused. The impurities have been diffused. So a part of the N region, which was there earlier, has been converted into P by adding the P-type dopants here. And so we'll assume that this is an ohmic contact. All right. We saw in earlier lecture how such a contact may be made. So this is an ohmic contact. It doesn't do anything to the PN junction except for it allows us to apply voltages and extract current here. And similarly, this is an ohmic contact. So the PN junction, the place where the real action takes place is between these lines here. And this is what is represented in this particular form here. Turn 90 degrees here. So this is what is represented. So as I said, we'll assume there are contacts at the end here and the contacts are here. We'll assume that the contacts are very far, which means that the region, N region that you see here and the P region that you see here, they're pretty thick regions here. All right. And contacts are ideal. All right. So we know what happens. And another thing that we'll assume that these regions that you see here, P region and N region, they're uniformly doped. Normally, when you add impurities from the top, when you try to diffuse them, the dopant density varies with position here. And often junctions are not uniform. The doping levels are not uniform. But to start off, to keep things simple and focus on the important concepts here, we'll assume that the doping here in P-type is uniform. Doping in N-type is uniform. And then what happens is, so in this P region here, as I go down, I have acceptors. And then suddenly, abruptly, my impurity changes to donor type here. Okay, and that's why we call this as a abrupt junction here. More realistically, it would, you start from P, acceptors are there, and the acceptor density decreases here, and the donor density increases here. So this is more like a more gradual junctions you will get rather than an abrupt change in doping. Okay, but we will start off with this particular assumption here. All right, so basic operation, all of you know. So let me go over it very quickly. We have for the sake of discussion, let's assume this is P-type and N-type here. We want to know what happens when you bring P and N together, and for the sake of discussion, we'll assume a symmetrical junction, 10 to the power 16 here, 10 to the power 16 here, where doping is same on both sides, except one is P-type, the other is N-type. And in that case, we know the simple picture that we carry in our mind about P-type is that is full of these acceptor ions, negatively charged acceptor ions, along with holes here. Oh, and because the doping is high, so what you would find is the hole density will be around 10 to the power 16, same as the acceptor density. The electrons would be Ni square divided by 10 to the power 16. Ni square is about 10 to the power 20. So N is about 10 to the power 4. So that's why in a picture, if you were to draw the picture, you won't even see an electron, right? If you have 10 to the power 16 holes and 10 to the power 4 electrons, you won't even notice. But I've shown you that there is an electron there. All right, it's there in this particular layer here. Similarly, in the N side here, a similar picture full of donor atoms, positively charged donor atoms, along with the electrons that they donated. So the electrons are all there. Overall, of course, the regions are neutral. So here we have 10 to the power 16 electrons, holes are 10 to the power 4 here. So imagine that you have this p-type and n-type. They were there separate, and then you put them together. Now you know. We can use animation to show what happens here, right? So this is what will begin to occur. Electrons will diffuse. I have a lot of electrons here, less here. The electrons will diffuse. Once they cross over the junction, they find plenty of holes, right? And we have seen recombination will occur, right? So they recombine quickly, and two things happen. This donor has lost his electron, and this acceptor has also lost his hole, right? So they have become uncovered. Earlier, the positive hole was covering sort of, and this region was neutral. Now the hole has been lost here, so this region becomes negatively charged. The electron has been lost here. This region becomes positively charged here, right? And all these things are happening close to the junction. That's where the gradients are, and that's where the action is taking place, right? So you end up with these charged region here. And as a result of the charged region, we saw that an electric field builds up, positive charge here and negative charge here. Note the direction of the field. The field will oppose movement of electrons from here to here, and similarly movement of holes from here to here. So it would sort of oppose, but the electric field is still not strong enough. So this process continues. Process continues here, and as it continues, more and more charges are uncovered, and my electric field becomes now stronger, and now less electrons will be able to cross over, and less holes will be able to cross over, and eventually, equilibrium will be reached, right? Equilibrium will be reached when there is no net flow of carriers across the junction here. And as a result of this, we have seen that what has happened is this region close to the junction here, which becomes depleted of carriers. This region has lost its electrons. It doesn't lose all of them, but the electron density here obviously becomes much smaller than electron density here. So this becomes depleted here of electrons. This becomes depleted of holes, and therefore we call this region a depletion region here because it's depleted of carriers. And another name for this is space charge region here. All right. So and of course all this is close to the junction here. As you go away from the junction, it's as if nothing has happened. The donors are there, the electrons are there, everything is the same away from the junction here. Similarly, the acceptors are here, the holes are here. Nothing has changed here. It's only close to the junction that things have happened. Radical changes have occurred, and we saw, as in the case of Schottky barrier diodes, we'll estimate what is the thickness here. You would expect maybe a few thousand angstroms or so. Okay, in that particular range. All right. So keep that in mind again to remind you that we say this region is depleted of carriers, but it doesn't mean that it doesn't have carriers. So don't make that mistake. For example, if you look at this picture again, we said far away from this junction, things are normal. Away from this junction, things are normal. So if you have 10 to the power 16 electrons here, holes are 10 to the power 4 here. If you have 10 to the power 16 holes here, you have 10 to the power 4 electrons here. So just focus on the electrons. If you have 10 to the power 16 electrons here and 10 to the power 4 here, so all around, if I start from here, I have 10 to the power 16, 10 to the power 16, same 10 to the power 16. The moment I start reaching now the boundary here, the electrons density. Oh, there's a problem here. This should be P should be 10 to the power 16 here, and so let's correct ourselves. So let's start with the hole density here. So hole density is 10 to the power 16 and remains 10 to the power 16. The moment you start entering, the hole density starts falling, keeps on falling. So it goes from 10 to the power 16, 10 to the power 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, and then it becomes 4. Right? So note the rapid changes in the hole density that is taking place here. Starts with 16 order of magnitude and then drops to the 4 order of magnitude here. All right, so it is rapidly changing in this region here. There are holes here. It's not that it's not there in these region here. There are holes here, except we say that this region, the hole density is small compared to the acceptor atoms here. Okay, so that's what we mean by it's depleted of holes, not that there are no holes or no electrons here. All right, so let's sketch the energy band diagram. This is something that we said is important. We had 2 lectures looking at it, so let's quickly do that. So we have p-type and n-type. As I said, a lot of it is revision for you. So again, as usual, what we do is we want to sketch the energy band diagram. So we imagine them to be separate first. p-type and n-type, separate them out, draw the diagram before equilibrium, and that starts off with E naught. Draw the vacuum level, locate where your p-type is. So locate that. It would be electron affinity below that, and then you know EC, EV, and Fermi energy, you know, depending on the doping here. So you locate this p-type here. Similarly, you locate the n-type here. Electron affinity, we are talking about both regions being same silicon. Electron affinity is the same, and then this is n-type, so Fermi energy is here. And from the doping, we can determine what the place of Fermi energy is. All right, so that's before equilibrium. After equilibrium, we know what will happen when we bring them into contact. This Fermi energy is higher than here. Electrons will start to go towards this particular side. So this is from the band perspective. Earlier, I was simply showing you, from diffusion and all that, drift diffusion, what was happening. So this is from a band perspective. We know Fermi energy is higher. Electrons will move from higher Fermi energy to lower Fermi energy. And as they move, this region will become positively charged. This region will become negatively charged. And therefore, there will be a field which will go in this direction here, pointing from right to left here. And because of this field, the energy bands will bend. And specifically, E naught will bend upwards like this here. It has to bend because that's how, remember, the electric field is nothing but the slope of vacuum level. And similarly, slope of conduction band also. So vacuum level will start bending like this here. It will start from here and bend up here, okay, to keep the slope negative. All right, so we start off energy band diagram in equilibrium by drawing EF. EF is constant throughout. We draw the junction, and then we locate these regions here, far from the junction here. So we say, well, far from the junction, everything is normal here. So EV, we know EV will be away from EF dependent on the doping level here. So we locate where EV is, and then EC, of course, becomes available. Similarly, we locate far from the junction where conduction band is depending on the doping. So we know this region here, then this is there. And then we locate, once we have this bands EC and all that, then we find where the E naught is. E naught is away by electron affinity here. E naught is away by electron affinity here. E naught is what we said there's no vacuum level discontinuity. We connect it in a smooth manner here. So we do that here. And then the conduction band would always be away by electron affinity here. So since the materials are the same, so it just connects smoothly here and it connects smoothly here. All right, so we end up with a energy band diagram of p-n junction in equilibrium. All right, one of the things that we see in the energy band diagram is that there is a barrier here. Why do I call it a barrier? Well, this is n-type. I have a lot of electrons here. For this electron to go over to the p side here, they have to cross this particular barrier here. They have to go up in energy, and going up in energy means encountering a barrier here for electrons. Similarly, I have a lot of holes here. The holes would like to go to this side because there are lesser number of holes here, but the holes again encounter a barrier here. For a hole, remember, going down in energy like this is difficult. For an electron, going up in energy is difficult. So this is the barrier that is there, right? And so built-in voltage. So we saw that the procedure for calculating built-in voltage, what we do is we do a law of conservation of energy. So what we do is, well, first of all, let's locate this point here. So depending on the doping, I know phi n, the separation between EC and EF. Similarly, depending on the doping here, I know phi p here, the difference between EF and EV here. So I know these values here. All right, so the way we start off, again, just to remind you, we start off from EF. We go around sort of loop and come back at EF, right? So that's what we do. So start from here, go here, add up the energy. Energy required is phi n. Then you go up here. You add up the next energy increment. The energy increment is Q VBI. Then you go left at the same energy. So there's no energy increment here, right? 0. Then where do I come down? I come down right to EV here. I come down here, subtract EG, the energy gap, and then I go up here, which is add up phi p. And then you're back at the same point. So just keep on adding. You started from here, keep on adding energies or subtracting energies as you start from this point and end up at this particular point here. That's all you have to do in any energy band diagram to get built-in voltages here. So if we do that, remember we added up phi n. So we have phi n here. We added up Q VBI. So we have Q VBI here. Then we move laterally, no energy, loss or gain. So there's nothing here. Then we moved down to Eg, minus Eg. Then we went up phi p and plus phi p equal to 0 here. And therefore, one can get an expression for built-in voltage. Built-in voltage is QVBI equal to Eg, energy gap. Well, the reason why Q is there because everything is in energy term. VBI is voltage. So voltage multiplied by charge gives you energies in electron volt here. So Eg minus phi n minus phi p. That's the most general expression for built-in voltage here. After that, assumptions can come in. Okay. So this is the general expression here. And then if we assume that my semiconductor is non-degenerate, then we know that, remember the expressions here, n equal to nc e to the power ec minus ef by kt. So we use that expression to write down phi n is kt ln nc by nd. That's where an assumption has already come in. The assumption that has come in is my semiconductor is non-degenerate, and therefore n equal to nc, that expression that we had derived, is valid. And from there we get a value for phi n. And similarly we get a value for phi p. Phi p is kt ln valence band density of states divided by the this thing here. So how many assumptions here? Actually there are two assumptions here. Which ones? One is non-degenerate, the other one, all donors are ionized. The expression that we have used is n equal to nc. So we've already assumed all donors are ionized, which is equal to nd. And similarly, all acceptors are ionized. So that's the another assumption that has gone in. And apart from non-degenerate semiconductors. Okay. So this is general. Okay. This is very general. But after that, there are assumptions here. Then, all I need to do is take phi n here and take phi p here and put it here. We get QVBI is Eg minus KT ln NCNV by NDNA. Alright, so this equation is fine. You know NC, you know NV, and if you know the doping levels, you can calculate VBI. But sometimes what we do is we put it in an alternative form by using the fact that Ni square is NCNV exponent minus Eg by KT. So what we do is from here we extract Eg. We write it as Eg as KT ln NCNV by Ni square. And instead of this Eg here, we plug this expression here. Alright, so we plug this here, and then so instead of Eg, we get ln NCNV, and then we get another expression which you will find more common in textbooks. VBI is KT by Q, ln NDNA by Ni square here. So that allows us, if we know temperature, of course, if you know the doping levels, ND and Na, Ni we know, and therefore we know the built-in voltage in a PN junction. Alright, so based on the two assumptions, non-degenerate semiconductor and all donors are ionized. Okay, so based on that, this particular expression is valid. If you have a degenerate semiconductor, suppose I had asked you to calculate built-in voltage for a P plus N junction. Okay, look at the word P plus N junction. P plus means heavily doped P region. So when you make P region heavily doped, what happens to this EF minus EV here? Becomes very small. And a good assumption is that phi p is approximately 0. If it's very heavily doped, EF will come and almost come very, very close to EV. So phi p is 0 here. Now I cannot, for that heavily doped P plus N, I can't use this particular expression here. For example, if I have doping of 5 times 10 to the power 19, I can't go ahead and put 5 times 10 to the power 19 here. Why? Because my semiconductor is degenerate. My EF is coinciding with the EV here. It's degenerate, I can't use this. You will get a wrong number. Okay, then I have to use this expression here. So in that case, it will be Eg minus phi n, and phi p is 0. So it will be equal to simply Eg minus phi n, and phi n is KT ln NC by ND. So the expressions, please keep in mind, it's always, whatever expressions we give, keep in mind what the assumptions are. Alright, so very often the mistakes occur because we use these expressions in places where we can't use them. So assumptions are very important to keep in mind. Okay, and in these cases, two assumptions are there. As I said, non-degenerate semiconductor, and everything is ionized here. Okay. All right, let me calculate. So as I said, we have an expression for VBI, so it's fine. But what I'll do is I'll still calculate VBI now using two more methods. Okay, just to show you how how we do analysis of semiconductor devices here. So similar in nature. So what I'm going to do is, everybody is familiar to show you application of this. So n equal to nc exponent minus ec minus ef by kt. That's a very fundamental equation in equilibrium, right? So we start from here. rather than adding up the energy increments and arriving at VBI, let's do it through a slightly different route. N equal to NC exponent EC minus EF by KT. So I can take a region like this here, somewhere here, and write down what is the electron density. So N is electron density, and capital N refers to that I'm here outside the depletion region, somewhere here in the N region. So N is equal to NC exponent EC minus EF here, of course, is phi N. So we write it phi N KT. Okay. Now, similarly, I write NP, N in P region here. So I'm looking at this region here in the P side. That's why it's electron density in P region and outside the depletion region. I'm not talking about depletion region here. NP will be equal to NC. Same expression holds, except that it is EC minus EF for this region here. EC minus EF for this region will be equal to phi N plus QVBI. So we write phi N plus QVBI by KT here, right? So this is the electron density in N region. This is the electron density in P region here. Relate them together. Very simple relationship. You get electron density in P region is equal to electron density in N region, exponent minus QVBI by KT. Now, can you see why we are calling it a barrier? I have electron density here. How much? Nn. What is the electron density here? Np here. And how is this electron density related to electron density here? Exponent minus QVBI by KT. It has to climb this particular barrier to reach here, and therefore is exponentially lower as compared to this here. Okay, so you see why we are calling it barrier. Similarly, I can write, I'm talking in terms of electrons, I could have talked in terms of holes also. In that case, what I would have found was the hole density in N region here will be equal to hole density in P region, which is here. Same, exponent minus QVBI by KT. The holes have to overcome this particular barrier to reach here. Okay, so similar expression we would have arrived at. Except that if we had started with P equal to NV, exponent EF minus EV by KT. Same route would have allowed us to obtain this expression. So if I look at this one, I can write now VBI is equal to KT by Q ln electron density in N region divided by electron density in P region here. So we obtain an expression for VBI. What is the electron density in N region? Is ND. And what is the electron density in P region? Ni square over Na. And therefore we substitute it here. And therefore we get the same expression for VBI. Right? So a slightly different route by starting from N, writing down what is N here, what is N over here. We have that and we relate them together. And then we know what is N here and we know what is N here. We know both the values here. N here is ND and N here is Ni square over Na. And that allows us to determine VBI also. Okay, an alternative route. A third route. Okay, third route to VBI. We start from current. Jn equal to Qn mu n, this is field, plus Qdn, this is a diffusion current, del n by del x. We are talking about equilibrium, so net current is 0. So let's put it to 0. Let's see how that leads us to VBI. So this is 0. All right, so let's now simplify. Let's take Q cancels out. Let's take n over to the right hand side and mu n also to the right hand side. So we get F equal to minus dn by mu n, 1 over n, del n by del x. What is the next step? dn by un is kt by q, and 1 by n del n by, this will become log. So, and further f I can write as minus del psi by del x. So I get here minus minus cancels here. dn by mu n is Einstein's relationship, kt by q, and this becomes ln x here. What will I do now? You want VBI, right? So VBI is psi n. Note, when you see a diagram like this, the N region is lower in energy, but N region is higher in potential. Okay, keep that in mind. It keeps on, often gets confusing. Sometimes we forget that it's an electron here. So this is higher potential here. So psi n minus psi p. So integrate it from here, kt by q. It will become ln n in N region divided by n in P region. Same. And then we know what it is, nd and ni square na. And again, we end up with the same expression, right? So we arrived from the current, and from current again, we arrived at this particular route here. Current is 0, so we arrive at an expression for VBI. Okay, so 3 different routes to VBI, And so a problem would be timely now. So let's calculate what is the built-in voltage. Okay, let's do it quickly here. So uniformly doped P and N regions, doping is given, symmetrical junction, Nd equal to Na equal to 10 to the power 16. We want to know what is the built-in voltage, and Ni is required. We'll take a value of 1.5 into 10 to the power 10 at 300 Kelvin. So our expression for VBI is kT by Q ln Nd Na divided by Ni square. So the purpose is that you keep a certain number in your mind regarding built-in voltage in a PN junction. So 0.7 is a number to keep in mind with the doping of 10 to the power 16. If you make it 10 to the power 17, 0.817. If you make it 10 to the power 18, 0.937. So roughly, for one order of magnitude increase, you're getting a 100 millivolt increase here. Can I do that now for 10 to the power 19? Can I substitute here? No, my semiconductor now will no longer be non-degenerate. So I can't do that. Okay, the next, so this is trivial. The aim is just to get the value 0.7, 0.817, 0.937 here. This is more interesting. Determine the temperature coefficient of built-in voltage. Temperature coefficient. VBI is here. First of all, is the temperature coefficient positive or negative? Temperature coefficient means as I increase the temperature, what is the change in VBI? Positive or negative? Positive. Ni depends on temperature. So the first, when we look at the expression, the T stands out, right? It stares at us. The T is here. So yes, VBI should be positive. But then we know Ni is a very strong function of temperature. So as T increases, this term increases, but Ni increases. So it's a question of which one is stronger. Nd and Na, we are assuming that they're all ionized, right? Let's say if I have 10 to the power 6, I'm talking about if I'm going from room temperature to higher values. I'm not going to lower. Okay, I'm not going lower. I'm not going towards 77 Kelvin and all that where donor freeze out and all that. I'm not going into that region. So, my diode is there. Normally, let's say at room temperature, things get hot. It goes to 50, 75. So I'm looking at that range. Okay. So which one is stronger? All right. So this is, of course, is direct. Ni square is here. Nc Nv exponent minus Eg by kT. Note that Nc and Nv are also weakly dependent on temperature. But the major factor is here, Eg by kT here. So this expression then actually, it becomes a little bit difficult to see what happens to my VBI as temperature changes here. A better expression which will directly give you, remember we had an expression like this, VBI equal to Eg minus phi n minus phi p. And if I take an expression for phi n and phi p, QVBI is Eg minus KT ln Nc Nv Nd Na. Now can you see clearly what will happen? As temperature increases, Nc Nv are very weakly dependent on temperature. So you can forget about it. Nd Na, we are saying they're all ionized. So now you see that as temperature increases, built-in voltage falls, decreases here. So this one is a stronger term. This is a strong, there's an exponential dependence here. This is what wins out as compared to this particular one. So how much will be the temperature depend? Now we can calculate the temperature coefficient. All I do is I take dVBI by dt, change in VBI with respect to temperature. So I take a derivative, and Eg does change with temperature, but very small. We'll ignore it again. Eg will ignore, NC and NV will ignore. The only temperature dependent term that we'll keep is T. And therefore it's very simple. The temperature coefficient will become del VBI by del T equal to Eg by Q minus VBI by T, approximately. So we calculated built-in voltage of 0.7 and Eg was 1.12 divided by 300 Kelvin, and we get minus 1.4 millivolt per degree Kelvin. Every 1 degree increase in temperature causes built-in voltage to drop by roughly 1.4. Okay. All right, so the next thing is, we said that there is a depletion region and we want to know what is the extent of the depletion region. How large is this depletion region here? Okay, so so what to do that, we need to solve Poisson's equation in this particular region. Okay, so these are very similar to Schottky barrier diodes that we did, except that in that case we had only one side of the junction. Now we have two sides here. So let's do that. So if I look at, this is the region where there are charges, and rho charge density here will be equal to Q. What are the positive charges in this region here? Donors plus holes, and negative charges are in general electrons. Now because this is still the N region here, we can neglect holes. So P0 is negligible here. Because we are talking about depletion region here, we neglect electrons also here, right? And therefore charge in this particular region is simply Q and D plus here. Similarly, when I go on this region here, the charge in general will be equal to positive charge, which is P0, negative charge, which comes from electrons and ionized acceptor atoms, N0 and Na minus here. We say this is depleted of carriers. N0 is anyway negligible, P0 also, because of depletion region approximation, is negligible. So rho here is minus QNA. And therefore, my charge in this volume charge density looks like this here. Constant charge ND till here, QND. And then this is where depletion approximation comes in, that it drops abruptly and charge becomes zero here. We have seen that the boundaries are not sharp, the boundaries are more diffuse. And as I've been saying, we'll look at the consequences of those later on here. Similarly, charge here is minus QNA and then drops to 0 at this particular boundary. Let's say the extent of this particular region is XP here, minus XP here. So that's the charge density, and what we need to do is solve Poisson's equation. Poisson's equation, which relates charge here to the potential, and so we have a region 1 and we have a region 2. In region 1, rho is minus Q and D here, and so we start, and electric field here is 0, no charges here. So we start integrating. So we get del psi by del x minus Q and D ES x here, integrate it once. We know electric field falls to 0 here. So we put at x equal to xn, electric field is 0. And therefore we get del psi by del x is Q and D, epsilon s, xn minus xn, straight. Okay. And the field then is minus of that, and field is then minus Q and D by ES, xn minus xn. Okay, so straightforward. Similarly, here we have Poisson's equation here. We integrate it once, we get the field here, and similarly the field here can be written in this manner. Okay, so straightforward, field here and field here, just integrating it once here. So the way it looks like is the following. The field looks, you can see here the field is changing linearly with x here. So it starts from 0 here, builds up here, and then starts falling again here, and then goes to 0 here. Field is 0 here. Maximum field occurs at the junction here, which makes sense. You have positive charges here, you have negative charges here. So maximum field lines will occur at the junction here, and so that's where the field is maximum. The field, of course, is continuous here. The same value of the field is here. So the field in region 1 at 0 must be equal to field in region 2. And so that gives us, when you equate the two field values at x equal to 0, it gives you ND into xn equal to NA into XP. This also, even without going through all of this analysis, we could have said that. Why? Because the overall p-n junction is neutral. Remember where these charges have come from? Initially, p-n junction was neutral, and then it was only because of rearrangement of charges that you get positive here and negative here, it remains neutral. And therefore, even without going into all of this, I could have said nd times xn, the area here, must be equal to Na times xp, the area here, they must cancel each other. Because overall, my p-n junction is neutral. All right, which is what you get from all this Poisson's equation and the field. You get nd xn is equal to Na xp. All right, so which tells you that once you know one value, let's say xn, then you know the other value also, xp also. All right, so nd xn equal to Na xp. The sum of these two regions is what we call as the depletion width, total depletion width, xn plus xp. And therefore, I can write from these two equations that xn will be equal to w Na by Na plus nd, and xp will be equal to w nd by Na plus nd. So if you know the total depletion width, then you know xn and you know xp. Or other way, if you know xn, then you know w, and therefore you know xp. So one of these things you have to find out, and you know everything else. Okay, so you know the extent of the depletion width. All right. Okay, let's look at this one. Look at this. So if you understand what has happened now, which side is more heavily doped? Suppose I give you a field like this. Why? What is the reason? Because overall is neutral, right? So nd times xn must be equal to Na times xp, and xp is larger, obviously. So we know here this relationship, right? We know that the nd should be more heavily doped here. So you are getting it from this one. What does the slope here indicate? Slope. If you see electric field versus x, what does the slope indicate? Note this equation. The slope of the electric field is equal to qnd. That's what the slope is equal to. qnd by es. All right, that's the slope here. And the slope here, qna. So the slope of this field versus Poisson's equation is, you can write it in terms of voltage or in terms of field. So the slope here indicates the doping. The higher the doping, you can see here, the sharper the slope here. And the slope here indicates again the same as Na. All right, so keep that in mind. In a field versus x plot, the slope indicates the Nd here. So if that is true, what does this indicate? Different? Yeah, but what kind? What do you conclude from here? You have, is this region uniformly doped? Yes, uniform because it's linear, right? If you take the derivative, so again, keep this in mind. Del f by del x at any point indicates qna. Q by es times na here, right? So it's, which means uniform doping here, right? Now here, is this uniform doping? Yes. And then this is also uniform doping. That's also true. The slope here is higher, means higher doping. And then the slope is lower, which means lower doping. So which means that close to the junction, I have some higher doping, and then I have some lower doping here. Okay. So and if I give you the number here and this, all these here, you can figure out how much is doping here and how much is doping there, right? So you can go back and forth here. All right. The next thing is, once you know the electric field here, which goes like this, and here, all you need to do is you need to integrate it once more. Once more, if you integrate, you get qnd by es xn x minus x squared by 2 plus c1 here. You take region 2, integrate it once more, xpx plus x squared by 2 plus c2 here. Now we know that at x equal to 0, the potential, whether I calculate from here or I calculate from here, the potential should be the same, which tells you that c1 is equal to c2. All right, tells you that. And also we know now that psi1 at xn minus psi2 at minus xp must be equal to VBI minus V here. Okay, and this is where I want to, I've written here VBI minus V, but I want to spend just next few minutes on this one here. Why have I written VBI minus V here? So this is the band diagram that we get in equilibrium, right? This is very clear. Now, suppose I apply a positive voltage to my P side here, and N side is still ground. Okay, N side is still connected to ground. P side I apply a positive voltage. What will happen to my diagram? Positive voltage here. Let's not worry about a junction first of all. Far away if I go, I have a semiconductor and I've connected it to positive voltage. All its energies will go lower, right? By how much? By the amount that I've applied here. So where if I go far away, note that what I should do is I should draw a diagram like this here, right? It will come down. By how much? By the applied voltage here. Right? So keep that in mind. If I'd applied and this side remains the same. I've not applied, this side is still connected to ground. Okay, so this side is connected to ground. This side has gone down by QB. And now what do? I connect it by a smooth curve here, right? And note that far away, my N-type will remain N-type. Nothing will happen here. So I can even draw a Fermi energy here, depending on the doping, the Fermi energy separation is okay. So now I connect it by a smooth like this here because this side remains the same and I connect by a smooth curve here and remains the same. What has happened to my net voltage drop across the junction? Net voltage here, it becomes VBI minus V. Alright, so that's the point that you have to understand. What is happening when I apply a positive voltage? My effective voltage becomes VBI minus V. If I had, on the other hand, applied a negative, this thing would have been up here. It would have become VBI plus V. Okay, in terms of, so this picture is important. When you apply positive bias or when you apply negative bias, what happens to your energy diagram? Okay, note that the voltage, effective voltage has become VBI minus V. Alright, and that's why to calculate depletion widths in general, what I am doing is I'm saying the voltage between the N region and the voltage in the P region here, Xn minus Xp must be equal to VBI minus V to keep it general. If I have equilibrium, V is 0. If I have positive voltage, V will be positive. If I had reverse bias, V will become negative. That's all. Okay, and therefore I will get a very general expression for my depletion width here. So all I have to do is take my expressions here that you see. All this was there. So I calculate psi 1 at Xn and psi 2 at minus Xp and equal to VBI minus V here, and therefore I obtain this expression, VBI minus V. And Xn we have already obtained earlier here, Xn and Xp we had already said. So all I do is I take Xn and put it here, I take Xp and put it here, and therefore we get this final expression, VBI minus V equal to Q by 2ES ND NA ND plus NA W squared, width squared. So all the terms you know the built-in voltage. And if your equilibrium, put V equal to 0, Q and ES are known, dopings are known, and therefore you have an expression for depletion width. You can find out what depletion width W is. And you can do that now at any bias. You can apply some forward bias here, V positive, you can apply some reverse bias here, and you'll get depletion width at any bias here. And once you know the depletion width, you know how much is the depletion region extent on the N side, and how much is the depletion region extent on the P side here. So all of these things you know finally by solving Poisson's equation under depletion approximation. So VBI we've already determined earlier, and now we know the depletion widths also. Okay, all right. So let me stop here.